Hello everyone, welcome back to Reverse Engineering Linux 32-bit Applications. In this video, we're going to start talking about the meat of this class. We're going to begin with stack buffer overflows, some of the oldest known flaws in software and something that's still very relevant today, where people are exploiting these problems in software out there. Now, in order to understand stack buffer overflows, we have to understand a couple of calling conventions. So we talked about this in the past. We said a calling convention is nothing more than a specification for how parameters are passed to a function. There are three common calling conventions that are used out there. cdecl, which is used by C programs primarily. Standard decl, which is another possibility. Fast call is a third possibility. So we will talk about these, and we will also talk very briefly about system calls in Linux. So cdecl, obviously this comes from the C language. So this is sort of the standard way that you call a function in C. Now, if you are using cdecl, all of the arguments to a function are passed on the stack. And the caller, not the callee, not the function that you're calling, has to clean up the stack. So these arguments are passed from right to left. And you might say, well, gee, this doesn't sound like a great deal for me because I have to clean up the stack. And why would I want to use such a thing? Here's why. If you have a method that takes a variable number of arguments, something like printf, you must use this method. So why is that? If I accept a variable number of arguments into my function, I don't really have a way of knowing what you passed me, how large it is, so I can't effectively clean up the stack. You have to do it. So that's cdecl. We also have something called standard call. Now this is a little bit easier in standard call. It's pretty much the same thing as cdecl. However, the callee cleans up the stack. Arguments are pushed from right to left, just as with cdecl. Now, this method cannot be used with a function such as printf that accepts variable arguments. And why is that? Well, we just said it. The callee has no way of knowing what you pass and how large it is, so they can't clean up the stack. So that's standard call. By the way, standard call is what is used in Windows. So if you look at Windows 32-bit applications and you make Windows API calls, standard call is what is used. Then there's fast call. How does fast call work? Fast call takes the first two arguments and it uses registers to pass them in. So ECX and EDX are used as registers to store variables. If there are more than two arguments to a function, the callee will clean up the stack. If there are additional arguments, once again, they are pushed in from right to left. I should mention this is one version of fast call. There are other versions of fast call out there, so this is not like the end-all, be-all fast call protocol. This is just one that you might see depending on the compiler that you're using, etc. So I thought while we were talking about this, we should also mention Linux system calls. Now, in the Linux and Unix world, if I call a kernel function, something that is built into the operating system, I am making a system call. In the world of Windows, I'm making a Win32 API call. And in Linux and Unix, I'm going to make a system call. And we'll see how that's different a little bit later. If you look at things like the assembly course, you will delve into those differences quite a bit. So a system call is made by passing a system call number in the EAX register. Then, if you have up to 6 arguments, they are passed in via EBX, ECX, EDX, and then ESI, EDI, and EBP. So they're using pretty much all registers. If you have more than 6 arguments to your system call, which honestly, I don't know too many system calls that would have that, then you will pass in the address for that in EBX. So for the most part, there is no stack involved with a Linux system call. Now, this is super, super fast. Recall that the registers are high-speed memory areas on the CPU itself. So when we're making a Linux system call, it is extremely fast. And this is one reason why if you run a Windows application on Linux using Wine, which stands for Wine is not an emulator, what Wine actually will do is translate those Win32 API calls into native system calls. So there are instances where programs will actually run better and faster on Linux than they do on Windows. All right, how do we successfully exploit stack buffer overflows? Well, the key is that we must overwrite the return address that's on the stack. On the stack, I've called a function, and it has created a frame on the stack. And in that frame, I have local variables, the frame pointer, and also I have the return address. Where do I go back to when this function is over? Quite often, we will also try to inject our shell code on the stack. It's not a requirement that we always do it this way, but it's a very common thing for people to try to do. A little bit more about the shell coding. Again, we do have an excellent course here on assembly and shell coding. I would highly recommend it if you want to learn more about this stuff. If you're just like, hey, I just want to download it and use somebody else's shell code, Shellstorm is a good place to look. So a little bit more about the stack. So as we said, we have to overflow the local variables. As a reminder, the stack grows downward in memory. So overflowing variables will also overwrite the return address. So if you look at this little picture I have here, I have my local variables, and then I have my frame pointer, EBP, which has been stored, and I have my return address. So this in the red is what I'm targeting. I want to overwrite this return address, and quite often I also want to write in some of my shell code, perhaps right after this overwrite. Yeah, that's a very convenient way to go if you can do it. And we'll see that there are some times where you can't do this. So One of the things that we'll see when we start getting into actually doing stack buffer overflows is that often what you have to determine is what's the spacing, what's the offset between this local variable here that I'm going to overflow and this return address. And we will see various methods of determining that offset. All right, so that is a little bit on the theory of stack buffer overflows. As a reminder, this is just one in a series of courses that we have here at Pen Tester Academy. And I look forward to seeing you in some future videos here in this course and other courses soon. So we'll see you then.